that we're sort of starting off with stuff that is a bit of a review from Wednesday's class. So I want you to add a few things to your notes. On all of your examples, A, B, C, D, E, I want you to write right beside them, describe the transformation. So write that beside everything. We'll do that as we go along because I want you to have the practice of being able to use language to describe the transformations as well as being able to do them. I'm going to do a couple of these real quick for you, showing you the different approaches students take. And then I kind of want to give you enough time today to work on that activity at the end. So today, we're going to continue with transformation of functions, but what we're going to focus on today is multiple transformations. So on Wednesday, we were either doing a vertical shift up or down, a horizontal shift right or left, or we were looking at our stretches and shrinks. Today, we're going to combine them together. We're going to do multiple transformations on one function. So it kind of is fun if you can let the anxiety go away a little bit. It's like once you get it, you feel like, wow, you mean I can draw this thing without like doing all these like tables or whatever? It really is kind of fun once you get it, but it does take a little bit of time. So here's we're going to call the square root of x our parent function, okay? And we're calling that function g. And we're going to be doing some stretches on this to sort of warm up today. So what is the domain of the function g? What is the domain of the square root function? You can either tell me by looking at the graph or maybe just from your knowledge of square root function. What would the domain be? In interval notation, what would it be? Anybody? Of my parent function, this one right here. Yeah, parent one. Can you take the square root of 0, Shane? Yeah. Some domain of g here? Bracket 0, comma, infinity, right. If you look at the graph right here, the graph starts at 0 and it goes all the way to infinity. Okay, so if you got the picture in front of you, you look at the picture. Otherwise, you say, what's allowed to be under here? Any non-negative number, real number. Okay, what's the range? What's the smallest y value you can have? Smallest 0, and it goes up to infinity as well. So that's the domain and range of my parent function. Okay, so here's my first transformation. Am I working inside before I take the square root, or am I on the outside after I take the square root? Am I inside or outside? I'm inside. So you know whatever's going to happen has to deal with a horizontal transformation. Okay? And remember that horizontal works counterintuitively. So when you see subtract 4, that means you're horizontally moving to the right 4 units. So to describe this transformation, there's several ways you can say it. You pick your favorite way. Some people like to say the graph of, that's my function called g, the graph of g, which is what's right here underneath. So if I put a little g on there to indicate that's the graph of g, my function g, the graph of g will shift 4 units to the right. He's always on time with his little cart. Do you mind shutting that door, Mary? Okay. The graph of g will shift 4 units to the right. All right? Some people like to say, another way they like to think of it is that they're going to add 4 to all x values. That's just another way people like to think of it. So if you think of this as our first description here, by thinking of the picture of the graph versus adding 4 to your coordinates, the second version here is where you would work with your tables like I have down here, which you can draw in a minute. Okay, the first version is more of a visual. So if you're thinking about just working with the graph If the graph isn't there, you can quickly draw a quick image of the square root of x down on your graph paper, right? You pick a couple of key points. So for example, you'd go to your original graph and you'd say, okay, when x is 0, the square root of 0 is 0. When x is 1, the square root of 1 is 1. And now you're going to pick perfect squares instead of dealing with things like square roots of 2 and 3. Then you go to 4. Square root of 4 is 2. You might work your way up to 9. Square root of 9 is 3. And then square root of 16 is 4. So you pick a couple of key points. I've got 5 here. You don't need to have that many. Because remember, when we're doing sketches of transformations, we're not getting each and every point exactly right. We're doing a quick sketch. So once you've identified your key points, you can just say, I'm just going to shift this graph 4 units to the right. So you pick a couple of the points and you literally move that point. I'm going to move 0, 0, 4 points to the right. So now I'm going to be at 4, 0. I'm going to take this point 1, 1 and I'm going to move it 4 points to the right. That puts me at 5, 1. And I'm going to take my point 4, 2 and I'm going to move it 4 points to the right and I will be at 8, 2. And I'll do one more. Let's do 9. 9 moves 4 points to the right, and I'll be at 13, 3. That's enough to get a quick sketch of my new function, my transform function. Okay. So now I just connect my points, and I go in the same direction as my parent function. And there it is. Okay, that's my transformation. So some people like working like that. Other people literally like going down to their table. They make a table of with the coordinates of their original function g, and they'll say 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. And then usually I would suggest putting it in as coordinates right beside it like this. I could have put in a third column here with the coordinates, but you can easily write it like that. And then they like to use these little arrows and they say, okay, I'm going to add 4 to my x values. So then they go ahead and they add 4 to the x values. So 0 becomes 4, 1 becomes 5, 4 becomes 8, 9 becomes 13, 16 becomes 20. And now when you take this new value of x and you put it into your new transformation, 4 take away 4 is 0. Square root of 0 is 0. Notice my y values are right back to where they were once I shifted this over. So then that's how some people do it. They get their new coordinates and then they plot them and they make their graph that way. Everybody does it slightly different. Some people will actually do a combination of the two. Okay, so that's pretty much how you do a simple transformation. Right. Any questions on that? All right, so the next one, we'll talk about it. We won't do it. Let's talk about this one. So first you look at your new function and you say, have I taken the square root of x? Does it look exactly the same? Do I see the square root of x there? You say, yeah, so I've already performed my function and now I'm acting outside of it. I'm subtracting 4 from all of my here's my original y values, the square root of x, and now I'm going to subtract 4 from them. So this becomes a vertical shift down 4 units. So my description is a vertical shift of the graph of g. That's my original parent function. It's a vertical shift of the graph g down 4 units. So that's how I use my language with my graph. If I were thinking about plotting points in creating tables of points and then showing my new points, I would think of it this way. I'm going to subtract 4 from all y values. Again, Do you like working with your tables or do you like working with your graph? So notice here, I've got the coordinates of our original parent function. We know we're going to subtract 4 from all the y values. So what are the new points going to be? Well, the new points will have exactly the same x values because I'm not touching my x values at all. I'm only going to change the values of y. So 0 now becomes -4. 1 now becomes -3. 2 now becomes -2. 3 becomes -1, and 4 becomes 0. So you can now take those 5 points, go right up to your graph, and you can graph them. Okay, I got to get my glasses for this one. Okay. Whoops. 1, -3, 4, -2, 9, -1, and then 16, 0, and that's a beautiful sketch of your transformation. Boom, you're done. Or you could have worked right on your graph and just literally moved the whole thing down 4 units. They both get you to the same place. It just depends on how you like to do it. Okay. All right, so those are pretty straightforward. We found out the vertical and horizontal shifts were pretty straightforward. Oops, how did I do that? I just lost everything. Wow. Just wanted to get to the next page. There we go. Oh, what's happening? Okay, so there's the next one. So how would you describe, put in here, describe the transformation? So someone want to give this one? What are we doing to the graph of G here? The graph of G, which is your square root function, what are we doing to the graph of G here in this one? Right, so the graph of G, you're multiplying all the outputs by 2. So if you're thinking about your y values, you're multiplying all y values by 2. That's what you would do to each individual coordinate, the y coordinate of every point, you would multiply by 2. What does that do? What kind of transformation is that if I ask you to describe the transformation? What's going to happen to this graph using the language from Wednesday's class? Vertical stretch, right? So the graph of G will be vertically stretched. Now, when we use stretches and shrinks, we no longer use the term units. We're always talking about a multiplier, either a multiplier by a whole number or a multiplier by a fraction. So in this case, we're stretching, so we're stretching by a factor, or you could say by a multiplier, whichever you prefer, by a factor of 2. So literally, here's the point 0, 0. When I multiply 0, my y value 0 by 2, it stays the same. Here's the point 1, 1. When I take 1 and multiply it by 2, it becomes 2. Here's the point 4, 2. When I take my y value 2 and double it, it becomes 4, 4. Here's my point 9, 3. When I take my y value 3 and double it, it's 6. Oops, glass time. Should have tried to make these coordinates a little bit bigger. 1, 2, 3, 4, 5. It's up here. Okay, so this is the last point, and now you've got enough to sketch that transformation. I missed that point. Okay. Shh. There we go. So what you notice is if you go to a particular point, here's your original point, 4, 2. You were at a height of 2 units above your x-axis. Once you do your transformation, you are now twice that vertical distance. You're 4 units above. Your height is now 4. So you've doubled your height above the x-axis. If you're ever in doubt, pick a couple of points on your transform function, like this one is 4, 4, and check it. Go into your equation and say, if I put a 4 in for x, will I get a 4 out for y? And check it. 2 times 2 is 4. Perfect. So you can always check your work to make sure that the coordinates of your new transformation is equal to the coordinates you would get if you literally plugged in points for x and out pops your y. All right, so I want you to try this one at your seats. Okay, folks, if you can't like see, what is it, the forest through the trees, what you could do is you could just start plotting some nice points, right? So in other words, you could say, if x is 0, what's y going to equal? What's y going to equal when x is 0? 0, okay? 0. All right. Now, if x is 1, and I take half of 1, I get the square root of half. I don't want to plot that. So you're saying, well, geez, originally, when I was 1, the square root of 1 is 1. But remember, you're acting on the input, and you're taking half of it before you take the square root. So if you want to get 1 for your output, what has to be true about the x value that goes in order to get 1 for your input? I can't put 1 in anymore because I take half of 1, and that doesn't give me this 1 for my output. It's got to be a multiple of what it went in as originally. And since I'm taking half of it, what do I have to do to x to get back to my original x if I'm going to take half of it? I got to double it. Shane's holding up 2 fingers. He's saying peace to everybody, right? So you've got to make your x values twice as big to get back to your original output, right? Because you're taking half of them now. You're acting on them. So if I want to be right here, if I want to be 1 unit above the axis, I got to go all the way out to 2 now. I got to go to 2 because now I say 1/2 of 2 gives me 1, and the square root of 1 is 1. So now I still have the same 0.00, but now I got to go out to 2 to be at 1. Notice they're at the same height, but look at their distance from the y-axis, folks. Look at the distance from the y-axis. The green point is only 1 unit away from the y-axis. How far is the red point from the y-axis? 2. So I've doubled my horizontal distance. When I compare those points, I've doubled my horizontal distance away from the y-axis. Well, let's keep going. Originally, I was at the point, let me put it with green, because green is going to be in my original parent function. When I was 4, and you took my square root, I became the number 2. But before I can become a 4 again, if you take half of me, and half of me is going to equal 4, what must the new x value be? 8, right. So I go out to 8 now, and half of 8 gives me 4, and the square root of 4 gives me 2. So my new points are 0, 0, 2, 1, and 8, 2. So I got to go all the way out to 8 to get to be the same height as 2. So that's going to be my red point. Okay. Now look at your distance from the y-axis. You're looking at horizontal distance. So you always go from your y-axis. On your original function, to get to the y value of 2, you were 4 units away. Now you're stretched way out twice the distance to 8 units away from the y-axis. Okay? So notice if you just do a little line showing your horizontal distance from here to here, the distance from 0 to 4 is 4 units. Now you are going from there to here. That's 8 units. So you've doubled your horizontal distance. Okay. That's called a horizontal stretch, folks. So this represents your original graph, the graph of G, has been horizontally stretched. How has that distance stretched? Whenever you describe a stretch, it has to be a number bigger than 1. It's been stretched by a factor of 2. Remember, you always divide, to get this number here, 2, you always divide this number by 1, which means take the reciprocal of whatever this coefficient is inside. The reciprocal of 1/2 is 2. Everything has to be doubled. Okay, so to get your final point here, you have to go out to 30. Let's see, how far can we? 18, right? I was trying to figure out how many spaces we had here. So half of 18 is 9, and the square root of 9 is 3. So now we have 18/3. So instead of 9/3, we got to go all the way out to 18 just to be 3 again. Okay, so now you have your stretch. This thing has been stretched horizontally by a factor of 2. So some people might say, can't that also be a vertical shrink? And it can be, but the factor of your shrink is very unfriendly. It's very unfriendly, the shrink. And I could tell you what it is, but you're not going to believe me. It's horizontally stretched. You believe me? All right. All right, these are reflections. You can do these on your own. Let's get to today's stuff, which is really the fun stuff. Sequences of transformations. Now, I saw Lenny do a look over to Adam like, oh, yeah, right. Multiple transformations. That's what we're doing. All right, so what can we do to our original function? So if our original function is f, we can act on the input of f 2 ways. We could multiply x by something and then add or subtract something from that. Then we could take that output and we could stretch it or shrink it depending on A, and then we could shift it up and down the axis. So this is the form of your function, your multiple transformations that your book uses. And if you have a function in this form, then this is the sequence, 1, 2, 3, 4, that you do. You do each of these transformations one at a time to get to your final transform function. Okay? So notice, this is a very particular form. So in other words, if you look inside here, your horizontal shifting is happening by this thing right, your horizontal shifting is happening right in here with this plus C. Okay, so C is acting as your horizontal shift. That's the first thing you're going to do, as long as this it has the form of bx plus c. And you'll see why in a minute, why I'm focusing on this. Then stretching or shrinking, well, you've got a couple of different possibilities here. If you're inside the parentheses, inside your function, then b is going to act as your horizontal stretch or shrink. Just like it did a minute ago when we had half x, the square root of half x. So this will be a horizontal stretch or shrink, depending on the value of b. Now notice these big brackets here are now taking us outside of our function. We've already performed what our function has said to do, and now we're acting on the outside. So A and D involve vertical transformations. So let's write that. B and C, and B and C, if I can write what I'm saying, that would be good. The values of B and C deal with horizontal transformations. The values of A and D involve vertical transformations because they're outside the function. Okay? We can be a little more specific. we can say what type of thing A does, what type of vertical transformation A does, and what type of vertical transformation D does. A will do a vertical stretch or shrink depending on its value. And D would be the last thing you would do. If you had a bunch of numbers in here and you think about order of operations, the last thing you would do would be to add the value of D. That's the last thing that happens. And notice in our sequence, the vertical shifting is the last thing that happens. So that's a vertical shift. Okay. So it feels a little scary to look at something like that. But I could make one up right now and we could talk about the values of A, B, C, and D. So let's scoot over to your next example real quick. Here's your next example. We're not going to do it right now. We just want to compare it. Our original function is our baby parabola, x squared. And here's your transform function right here. So you say, okay, because I see something square, I know my parent function was the parabola. It's going to look a little different. I've got a lot of things going on. So if I write right above this, y equals a times, now notice my function is called j. So instead of putting an f there, I'm going to put j of bx plus c plus d. So can someone tell me the values, or any one you want, any one of these values, can you pluck out from our transform functions what A, B, C, or D is? Just pick one and tell me what that value would be. What would D be here? Or what would C be? Or what would B be? Or what would A be? Just find whatever one's easier for you. C is -4. I should have written this as bx minus, okay, -4. All right. Okay. B is 2. Okay. D is 3. And what's A? 1. So you could have a 1 out here. All right. So I really should have written bx minus c. I'm going to go back. And the reason I'm doing that is I don't want to confuse you with your heart. So I'm going to put here minus. And so that means we just shift this to a minus. So now you can see C is the number 4 because you're subtracting 4, right? You're subtracting 4. And that's what that's how you're used to thinking of your horizontal shifts. All right. So look, A is 1. And what was the A outside of everything? That was talking about vertical stretches and shrinks. So none of that is going on. You don't have to worry about vertical stretches or shrinks. So nothing to worry about here, nada. D talks about a vertical shift. So since D is 3, you know at some point you're going to move your entire graph up the y-axis 3 units. So this says vertically move up 3 units. Now, all the tricky stuff happens inside your function. That's all your horizontal stuff. That's the B and that's the C. So when we see take away 4, it acts just the opposite of what we think. We're going to shift to the right 4 units. So this is shifting right 4 units. And again, your x is being doubled. So think of it, it's just the opposite of the one we just looked at. X is being doubled. So to get back to the original x, to get back to 1x, not 2x, what would you have to do to all your x values? To get from 2x to 1x. Divide by 2, right. or multiply by the reciprocal of 2, which is 1/2. So this is going to be a horizontal shrink. So B tells you to, as using Kate's, divide all x values by 2, or that means horizontally shrink by, it's got to be a fraction, 1/2. So those are the 3 things you're going to do to your original x squared function. All right, so let's do them. How are we going to do them? Where do we start? I don't know about you, but I like to have my parent function somewhere on here. All right. The other thing I'm going to do is, I notice, just so I don't, someone in my last class complained a little bit about not being able to see things. So, or not complain, just asked. She didn't complain. She just asked if I could make it bigger. I really couldn't. I was trying to do everything on one graph. So I just made 2 more graphs here. So the first, I have to do 3 transformations. So notice I want to start with my parent function and then have 3 new graphs. So my parent function I can almost do in my sleep as you can: x squared 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. So just do a quick sketch of your parent function just to start off. Okay. There you go. Here you go. So there's a quick sketch of my parent function. You do a quick sketch as well. All right. There we go. Now, on your parent function, identify some key points. Key points. Now, what are key points? You can pick any key points you want. As I look through here, I can see that I'm going to have to take my x values and divide them all by 2. So I'm going to pick some x values, some original points where my x values even, so I can do that easily. So I'm going to, instead of picking negative 3, 9, I'm going to pick the point negative 2, 4 as one of my key points. So I might as well take its opposite across the y-axis, 2, 4. I'm going to take 0, 0. Maybe that's all I need. We'll find out. All right. So if you go back to the previous page, it tells you there's a sequence. When you have your equation, your transformation in this form, I keep saying that. Pre-calculus is going to look a little different, and I'll show you in a minute. When it's in this form, notice the stuff inside the parentheses. Here's the key, folks. See how the stuff inside the parentheses, if you wanted to, you could factor that by pulling a common factor of 2 out. There's no factoring inside. So when it's in this form, the first thing you do is your horizontal shift. That's the first thing you do. So what are we going to do? We're going to take this entire parabola and we're going to just shift it to the right 4 units. I know I said parabola instead of parabola. I know, my Boston accent. Make fun of me, Shane. That's fine. Okay, so you're going to take each. Do you have to do every single point? No, just do a couple of your key points. So instead of 0, 0, I'm going to become now 4, 0. Here's my first movement. Instead of negative 2, 4, I'm now going to become, I shift my negative 2, 4 units to the right, I become positive 2, 4. There I go. And my 2, 4 shifts 4 units to the right, I become 6, 4. That's all I need. Boom. I'm just doing quick sketches now. Here we go. Some people like to do this. They like to take some of their original points like this. I just want to give you like the flavor for all the different ways you could do. So they take their original points and then they do these arrows like this. And they write above it what they're doing, add 4 to x values. And then they just do that, 2, 4, 3, 4, 4, 0, 5, 1, 6, 4. Right? And then they plot those points. All right. Now, what does our sequence of transformations say to do next? Any stretches or shrinking, any one of them. Well, we don't have any vertical stretching going on because the number outside of my function is 1. So I go inside my function and I say, oh yeah, I have a 2. So that means I think the inverse, which is 1/2. I divide all my x values by 2. I'm going to do a horizontal shrink. So again, put your key points in here, 4, 0, 6, 4, and 2, 4. Notice I picked the even ones. Okay, and now what are we going to do to them? We're going to take all of the x values and we're going to chop them in half. So instead of 2, 4, I am now going to be 1, 4. I'm going to divide all my x values by 2. And instead of 4, 0, I'm going to become 2, 0. And instead of 6, 4, I'm going to become 3, 4. So those are my new points to graph. I move down. You could do it right on, you only have 2 graphs. You can do it right on the same graph right now. I'm just going to scoot down. So I've got 1, 4, I've got 2, 0, and I've got 3, 2. So this whole graph now is happening in a much narrower space, right? Okay. So that's my next transformation. I only got one transformation left, folks. That's my last transformation. So let's put my key points in here, 2, 0, 3, 4. And what was my other one? 1, 4. Notice usually 3 or 4 points will do you. All right, so let's put those points in, 2, 0, 1, 4, and 3, 4. Those are my new points. And now I look up to my equation of my graph and it says the last thing I have to do is I have to add 3 to all my what values? What is that plus 3? What kind of thing is that? I add 3 to all my outputs. So I add 3 to all y values now to shift this thing vertically up. So 2, 0 is going to become 2, 3. 1, 4 is going to become 1, 7. And 3, 4 is going to become 3, 7. So I literally just move up 3 from where I am, and I draw my new graph. And here it is. Here's my final graph right here. And you say, how do I know if I'm right? Check. Here's your function. 2x minus what? 4 squared plus 3, right? So pick one of your points on your final graph and check it. One of our final points here is 2, 3. So y is 3 when x is 2. Well, let's see if that works. Okay, 2 times 2 is 4. 4 take away 4 gets squared, and then 3 is added to it. That's 0 plus 3. That equals 3. You're a happy camper. Okay? So that's how you do your transformations. You take them one at a time. You can do tables. You can do whatever you want. Okay. Now, what else did I want to say here? Here's the last thing I want to show you. And this is for those of you who are going on to like pre-calc and you're going to do a lot of transformation. You'll see transformations over and over again in pre-calc, but with trig functions. So I want to take this equation right here and change it a little bit for you. Y equals 2x minus 4 squared plus 3. You can pull out a common factor of 2 inside those parentheses. And this is how most of your stuff will, what most of your functions will look like in pre-calc and calculus. They'll have this form, a, and then they'll have a function, and then inside the function, the b will be outside. Okay, notice it will be outside of x plus or minus. Now, sometimes x is just x because c is 0. So there's a little, so you look at these two and you know mathematically they're the same. The only difference between what your book is telling you to do, because your book is giving you a recipe, and the recipe works as long as everything is in this form. In other words, it doesn't have this form right here with a common factor out front. When you have this form, you do all of your stretches first and your shrinks first. So if you have a horizontal and a vertical stretch or shrink, you do those first. Then you do your horizontal shift, and always your vertical shifts are last. So if it's in this form, you do vertical and horizontal stretches and shrinks first. Then you do your horizontal, so that's first. Second is your horizontal shifts, and finally is your vertical shifts. So this is, if you want to become like really good at this, I would suggest, we just did this transformation. You know what it looks like in the end. Now do this one, which is exactly the same. So you should get the same final graph, but you're going to do the sequence a little bit different. You're going to do your horizontal shrink first, then you're going to do your vertical, your horizontal shift, but notice it's no longer to the right 4, it's to the right 2, and then your final vertical shift up. And you'll get exactly the same answers. So what I'd like you to do now is I'd like you, and it might be hard, we'll start this first one together. We'll draw the piecewise together. We'll do the first transformation, and then I want you to practice doing the rest of them at your seats. So we got a piecewise function. What's the domain? The domain, the first part of my domain starts at 0 and goes to 3. And that tells me when I'm 0 to 3, I am going to be this constant function 3. And you say, wait a minute, you're not 3 at 3 because it's not defined for 3. But look, jump down to the next step. When x is 3, you get negative 3 plus 6. That's also 3. So that's the first part of my piecewise function. The next piece is just a linear line with a slope of negative 1. My final point is going to be at x equals 6. So when I put 6 in here, I get negative 6 plus 6 is 0. So I go like that. And then I just do a slope of negative 1 straight down like that. So there's my graph of k. So this is the graph of k. Pluck out some key points if you want. You could say 0, 3, 3, 3, 5, 1. Pick whatever point you want. 6, 0. You could have picked 4, 2 if you wanted instead of 5, 1. It doesn't matter. Or you could do a little table like this. X, 0, 1, 2, 3, 4, 5, 6. 3, 3, 3, 3, 2, 1, 0 is k of x. And then you can put your points 0, 3, 1, 3, 2, 3, 3, 3. Gets a little boring when it's constant. 4, 2, 5, 1, and 6, 1. 6, 0. Okay. So when you look at this function, you say, okay, what's happening? Inside the parentheses, my value of b is 1. No horizontal stretching or shrinking. That always confuses me, so I lucked out. Minus 1 tells me I shift right 1. Yes? So I'm going to take this entire blue function, and I'm just literally going to shift it to the right 1 unit. So that means I add 1 to all my x values. So if you have a bunch of points already labeled, you can literally just change all of your x values by 1. I'm just going to pick a couple here. My y value is not changing at all. So I start at 1, 3, I go to 4, 3, I end at 7, 0, and then I shoot right down with a slope of negative 1. There's my first transformation. Done. I've taken care of the shift right. Now look, you're now acting outside your function. So the last stuff you have to do are vertical transformations. You've got the 1/3, you got a reflection, and then you have a shift. So take that function, take some key points on here, and perform each of these 3 things, and this is the order you'll now do it. This is 1, 2, 3, and 4. And see if you can come up with a picture of that transformation. And I'll help you out. Once you do that, you can start your activity for the day.